Can I?
Yes, sure.
Okay, good. Okay, so thank you, Amirali, for accepting the invitation. We are pleased to hear you today, and you will talk about the stochastic thermalization of a discrete nonlinear Schrödinger equation.
So I want to thank the organizer and Mariel for the invitation, and I'm very happy to talk here. So I prefer to turn off my video because I probably have unstable connection. But if at some point you lost me or you couldn't hear me, please let me know. Okay, the thing that I will talk today will be a joint work with my advisor Stefano Olla from Paris, and it's about the stochastic thermalization of the discrete nonlinear Schrödinger equation. So the plan of the talk is as follows. So Mariel told me that the audience will be mostly PhD and master student, but probably it's not the case. So I prepared a rather long introduction about nonlinear Schrödinger. It's not completely related to things that I will do later, but since the audience are mostly from probability background, I think it's nice to give some background about the nonlinear Schrödinger and some basic facts that I will use some of them, and I think I will try to motivate why I'm interested in such a problem in the first section. Then I will tell you about the model that we studied and the result that we have, and finally I will give some heuristics about the proofs and some remarks. So the nonlinear Schrödinger equation is the following. For me, is the following dispersive equation. So I have a function that is in d space dimension. So omega is a space. For me, I either take it R or the torus in d dimension. And here is a time derivative. Here, gamma is a Laplacian on omega d. And here I have a nonlinearity, which is a form of a pure point, power point. So this p is usually greater than 1, and it determines the power of the nonlinearity. And this kappa is either 1 or -1 for me. So these two regimes will be very different. So kappa -1 is the thing that people call focusing, and kappa equal to 1 is the thing that people call defocusing. And later, probably it will become a bit more clear why. Of the equation for different kind of nonlinearity, about the blow-up solutions, about the Gibbs measure of this equation that I will talk a bit more about, the discrete version of this. So these are rather like famous book in this field. Okay, so this equation has two important conserved quantity that I will be interested, and I will be recalling them over again. First is the energy. So you have a kinetic part and a potential. And the second one is basically the L2 norm that I call the mass. So it becomes a bit more clear why different sign for kappa give you different. So when kappa is positive, the kinetic and potential part has the same sign, but when it's negative, they are competing with each other. So we'll force, they want to drive your system to two different rather behavior. One of them is some kind of a dispersion, and the other one is like concentrate over a small point. So one of the important question about this question is the lifetime behavior. How does this equation behave as t goes to infinity? In the defocusing case, when kappa is equal 1, for many initial condition, basically for most H1 initial condition, people when you have like you write your equation over the whole domain, you expect to see some dispersive behavior. And to have an idea of what do I mean by dispersive, it means that if you take any compact set of your domain and take the mass over that compact set, this mass will be 0 as t goes to infinity. So somehow your field is escaping to infinity, so that there will be no mass in like compact sets as t goes to infinity. But in the, this is not defocusing, this is focusing. In the focusing case, so this regime is called like subcritical when the power of nonlinearity is less than 1 plus 4 over d. So this is not a d here, this is like only focusing. So in this regime, we have like global well-posedness for the equation. So the equation is well-posed for any time, for initial condition in H1. And you can show that you do not have this dispersion anymore with a special class of solutions that people call them like solitary waves, or when you are in the periodic case, they call them periodic wave. So you take a positive omega, and so these are time periodic solutions. So you have this anastas, and you put it inside the equation, and you will see that this function that does not depend on t should satisfy the following ODE. So we can construct solutions that does not disperse. They have a positive mass over some compact place, and they do not go to infinity. They are oscillating there. Okay, and this ODE is studied rather well in the literature. So when omega is r in this subcritical regime, you can show that every real positive solution is a shift of some a smooth radial profile. So, and people call this like ground state solitone, and it become a bit clear later why the name ground state is coming. When you pose this equation over a periodic boundary, over a periodic set, then the study of this equation is much harder, and there are not many results in the literature. There is some specific case that we will be interested later, and I will come back to this with a bit more when we are in one space dimension and the nonlinearity is 3. Then you can solve this equation rather explicitly on form of some functions that people call them Jacobi elliptic functions, sinusoidal and dinodoidal functions. They have some explicit form. And you can show that, for example, the uniqueness of a non-constant positive real solution. So if you have this equation and you assume that phi is positive and non-constant, then you will have only one solution if you fix the mass. Okay. The reason for the name of ground state is that you can have some variational characterization for this object. And the variational characterization will become important later for me, is as follows, is that if you take the following minimization problem, so you take the minimum of the, so recall that for me H is the energy, and here I'm in the focusing case, meaning that this is negative. You take the minimum of this energy over the all H1 functions that have a constant mass m. And I call this value like I of m. And I'm in the subcritical regime. Okay, the reason that I'm calling this subcritical, I will comment on that later, but remember that this is a regime that I have a solution for any time, and so on. So if I consider the following minimization problem, this minimization problem has a unique minimizer up to 2 symmetries. So notice that if I multiply this psi by constant phase, so a phase that is constant over all the space, or I move it by some, or shift it by constant number in space, then the energy and mass does not change. So basically energy and mass are blind to these 2 symmetries. But the good thing is that this minimization problem has a unique solution up to these 2 symmetries. The same thing is true when gamma is this should be R, sorry. The same thing is true when gamma is equal to omega is a torus. In this case, Okay, this result is rather in the literature for only d equal 1, because the wealth of the knowledge in the literature is much scarce comparing to the when the domain is R. And okay, in this paper, people prove that this minimization problem has a unique minimizer, and we have like a continuous phase transition. When the mass is less than some constant value, this minimizer is a constant function, and when it is bigger, then we get some explicit functions. In both of these cases, we have a compactness of the minimizing sequence in the H1 up to these two symmetries. So, and this compactness is derived by something that people call concentration compactness arguments that is go back to Lyon's. So basically, this argument is saying that okay, since we are not in a compactness, since we are in like H1, we do not have compactness, but the scenarios for non-being compact are limited to certain small scenario that, for example, your field is vanishing, or it moves to infinity, or it has a very harsh oscillations. But if you add the conservation law of your equation to these three scenarios, you will see that it cannot be possible, so you get compactness. So it's important to remember that these minimization problems, so these ground state solitones, have a compact minimizing sequence. And from this, for example, we can deduce something that people call orbital stability. So what does it mean that orbital stability? It means that, okay, if I start with some initial condition which is close to these solitones, then if I wait at long time or at any other time, I will stay close to these solitones up to these two symmetries, up to multiplying by a constant phase, the phase that does not depend on the point in the space. So it's a global constant phase and a global shift. So only using the compactness of the minimizing sequence, you can basically deduce, and using, of course, the conservation of the equation, you can deduce orbital stability, meaning that if you start close to the solitones, you will stay close to solitones at later time. Okay, these orbital stabilities are nice for people, but they are interested in like rather stronger results that which they called asymptotic stability in some functional space. So here you can think of T, meaning that if you start from any initial condition, is it possible to show that asymptotically after, as T goes to infinity, you will be close to these solitones? So these are like among major open problems in the field of dispersive PDEs that people want to know that. So this concept of solitone can be defined for rather more general dispersive equation like KdV equation, NLS, and so on. But these type of questions are questions that people are rather interested, that you start with any initial condition and you can show that as T goes to infinity, you converge up to some in a proper norm to these solitones. And there is a more stronger notion, is something that people call solitone resolutions. The solitone resolutions is basically saying that in like, so in RD and for like subcritical regime, so any long time behavior can be decomposed into some solitones and some dispersive parts. So you can decompose your profile as T goes to infinity into some solitones that are moving with different speed, that are oscillating with different speeds, and another part which is vanishing in L2 norm, for example. So this is rather a very big open questions in this field, and people are interested to understanding this kind of behavior in like for NLS and so on and so forth. Good. So, okay, I'm not analyst, so I do not want to answer these questions from a conventional point of view, but I want to cheat a bit using some probability and so changing an equation a bit by adding some stochastic noise. So the basic motivation that comes further is so basically these behaviors that at long time you will see only solitons in these equations is behavior that people see in numerics, people see in the nature. And I want to say that, okay, I won't answer this problem mathematically completely. I will try to add change my model a bit, add a very small noise, a small stochastic perturbation, such that this stochastic perturbation provide such qualitative behavior at long time for me. So basically the motivation comes from here, that I have this kind of behavior and I want to introduce some stochastic perturbation that can recover this general behavior. Okay, just let me give you a bit more motivation. So the way that I want to look at this problem is going through the Gibbs measure. So okay, probably I want to change gear a bit and talk about something a bit unrelated, but it becomes clear why I'm interested in that. So for the equation that we were observing before, you can think of the Gibbs measure of this equation. Why is that a relevant object? That's a good question, but it turns out that later people understood that this object have many applications in the different directions. So you can simply take e to the minus beta h and okay, you product over the, so it's a completely formal object, and you want to study this object. So the first question probably for a mathematician is that how to make sense of this object. Part, and then you absorb this into this formal measure, and this gives you some sort of a Brownian bridge on the torus. So this measure, at least in d equal 1 for probabilist, is something very well understood. Then you have a problem that, okay, this potential here is negative, which means you get some positive rate, and you can circumvent this by going to some sort of a or like condition your measure to have certain mass. So if you condition your measure having certain mass, then using an interpolation equality, which people characterize the Nuremberg inequality, you can observe that this potential part will be bounded by the gradient times the mass to certain powers. And these powers remain positive and good in the subcritical regime, namely the regime that p is like less than 5 in dimension equal 1. So in that sense, if you restrict this measure into the subspace that your measure is less than some constant, then there are many works that people try to prove that this measure exists, like in okay, wait, Claudio, do you still hear me?
Yes, I do.
Yes.
Sometimes
okay.
from time to time you're cut, but yes, I do.
Very
okay,
few. Yes, it's okay. We can understand. We can follow.
Okay. Let me see if I can do some. Okay. So the questions that, okay, if you see that it's become some sort of incomprehensible, please maybe I can try to some internet or do something. Okay, the questions that, for example, people ask about this measure is about the existence of this measure for higher dimension, that's like it's connected to renormalization, or they ask that is this measure invariant under the flow of the Gibbs measure. This is like many work of Bourgain and others. Or this measure become interesting for mathematician because so in certain rough initial data, for example, for HS solve of a space S less than 1, the equation is ill-posed, but you can prove that is well posed almost surely with respect to this measure. So for almost all almost all initial condition, which almost all should be understood with respect to this measure, this equation is well posed for much rougher initial data. So it is proven to have many applications in different parts of mathematics, and the behavior of itself. So how does the large deviation of this and how does it behave itself is rather interesting. It's working the way that so the way that waits that okay moment we looking at some measure infinite dimension, this Gibbs measure are the long time behavior of Hamiltonian dynamic system, knowing that this if you assume that your system ergodic, which is something very hard to prove usually, you can show that the long time behavior is usually governed by this Gibbs measure. So in that sense, we want to use this idea and add our stochastic perturbation such that it makes the less ergodic somehow, and it thermalize it. So we converge to a Gibbs measure that represented some temperature. Good. Okay, this is hard to do in the continuous setup, so we huge simplification by discretizing the equation. But for many of the applications, the discretized version in the regime that we are interested that are really a good approximation of the continuous version. Okay, so let's go to the model that we want to study. So the configuration space for me would be like C to the N or so. So I take basically the discretization over the discretization of the previous equation. And here for me, this gamma would be the discrete Laplacian. So now I'm looking at this huge system of ODEs, which is much nicer mathematically. And okay, I rescale this. So for the moment, we should not care about this, but you should rescale this. You can rescale this Laplacian differently. So in the continuous limit, you have different problems, or either you are approximating the torus, you're approximating a growing and like a fixed buck which grows with certain rate, or you're approximating RD. So this corresponds to how does you rescale this mesh size. But for the moment, I don't care about that, but take them as some constant. Again, we have the same behavior of focusing and defocusing. And so for me, this is a discretization of the NLS on the box of length NH. So you can see it as a Hamiltonian dynamics with Hamiltonian and mass, which Hamiltonian is basically the discretization of the previous Hamiltonian, and the mass is basically the discretization of the previous mass. Here I'm okay, I will choose this parameter later whenever I want to approximate a certain continuous problem. Okay, then the generator of this dynamic, okay, I write, so now, okay, probably for just for the matter of notation, here from this slide away, X is moving on a torus, on a discrete torus. It's not a continuous variable anymore. And Y as well. So now I'm in a discrete setup. So all my variables are discrete unless I'm explicitly stating. So I can write this psi into a real and imaginary part, or into the like amplitude and a phase. So writing it this way, then the generator of the Hamiltonian dynamic can be written as this way. I will denote it by A. Then the stochastic perturbation that I was trying to advertise from the beginning have the following form. So I have a diffusion. So this partial derivative is a partial derivative with respect to the phase of the particle number x. And okay, I take this like the diffusion operator. So I put some independent diffusion over each point in the space. I will have the form of my generator if you open this derivative somehow. To have another view, if you write the system of a stochastic differential equation generated by the Hamiltonian dynamic and the noise, then you will have this term. So first you have the linear equation, then here you will have a multiplicative noise. Here is like basically the autocorrection that is given. So okay, here for me that okay, this should be x and w are set of processes. The thing that I want to emphasize, so for example, if you are interested
Amirali?
okay, can you hear me now?
Ah, yes, now yes.
So how long asked me?
Just a few minutes, really a few seconds, I would say.
Okay, few seconds is much better, but few minutes
Yeah,
probably.
few seconds.
Okay. So, okay, for people who are interested, for example, in stochastic PDE, then this is a very bad news because this the derivative here is extremely rough. It's so for example, there is basically no way to give meaning it with these tools of like regularity structures or per control distributions. But in the like a discrete setup, it's a nice system of stochastic PDEs, stochastic differential equations. Sorry. Okay. So let me tell you about the properties of this. The first thing, if you apply this to everything that is a function of amplitude, it gives you 0. So in particular, for the original equation, dynamic that is generated by Hamiltonian dynamic conserved. So on a compact manifold by this. The second thing is n is hypoelliptic or Hormander bracket condition and uses good set of commutators, which is a bit more complicated than usual setup that people do in like adding noise to the moment. Sorry, separators. We'll see that Ln is. Then you will see that this Gibbs measure, Ty's version of this Gibbs measure that I show you invariant for this dynamic.
Okay, we lost Amirali once again. I'll write him an email. Okay, so I wrote an email to Amirali.
Mariel, can you hear me?
Yes, now yes. But yeah.
Now yes. Okay.
Yeah.
This time it was still a couple of. Okay,
yeah.
I changed my connection.
Okay.
But okay, still it's bad, no?
For now it's okay, but we don't have your screen for now.
Okay. Let me share. I think it's the effect of extreme cold wave here. Everything is freezing here in Belgium. Like exactly. Electricity is internet. Everything is freezing.
Yes.
So it's not compatible with this temperature, I think.
Yeah.
Okay. Okay, can you see it now? Mariel, can you hear me?
Yes, we can see it.
Okay, you can see it. Okay. Okay, I'm really sorry. It was usually a good internet connection in the previous days. Okay. So you see, using this previous so
from me, but I don't see it yet.
You cannot see my screen?
No, I can. Mariel, it's now you that have.
Okay, so this
I can't hear you actually. Go on, Amirali.
Okay, let me ask you. It was only me that was hearing Mariel bad, or no? You were hearing her bad too?
No, she has having problem. We can hear you perfectly.
Okay, good. I swear it's a problem of Northern Europe and the cold. Okay, so let me recall the observation that probably you missed because of the connection problem. So I was saying that this generator conserves the mass. It's hypoelliptic. The Gibbs measure, which is a discretization of the previous Gibbs measure that I show you. So I have a normalization factor. I have the energy that I show you previously. And this is a uniform measure on the sphere, which a sphere of the fixed mass. Then this measure is invariant for the dynamics because of the way that I construct it. You can see by doing some integration by part. It's invariant, and more importantly, it's a unique invariance measure. So if I had time, I probably can show you why it's a unique invariance measure. But combining this observation, so the hard task was how to come up with things that have these properties all together. But having these properties all together, then it's rather classical to see that this measure has some mixing property, meaning that if you start from any initial distribution for your process, you will converge to this exponentially fast for fixed n. Of course, I should say that here this convergence, it's like that all these alpha and c are depending on n. So you should be careful if you want to take limits of n and so on and so forth. Okay, so let me give some remarks. If you have seen the work concerning the stochastic Schrödinger equations, then the nice thing about the dynamic is that it's mass conserving and it's thermalized the system. So it's something that's rare to see, because usually people, when they add mass conserving noises, like in this equation, they do not thermalize the system. But if they thermalize the system, they do not fix the mass. They do not keep the mass conserved. So they should use the grand canonical measure, or then, for example, for a focusing case, they will have problem for the construction of the measure. So the nice thing is that it has these two feature simultaneously. And okay, these features are true for a general class of nonlinearity. So you can take any function of the amplitude for the nonlinearity, and because of the form of the noise that I show you, still the same observation remain true. So let me, using this noise for my new dynamics, I prove or at least show something very similar to the asymptotic stability that I showed you previously. So I fix a setup. So I take nonlinearity equal to 3 in a cubic case. Sorry, it means cubic in a Fukusin case, in dimension equal to 1, and I take those parameters such that my Hamiltonian and mass or discretization are of these two continuous objects. Then the minimization problem that I showed you previously has a unique minimizer with a compact minimizer, as I told you before, and you have an explicit form of this minimizer. Okay, let me do a sanity check. So Claudio, you are still hearing me?
Yes, perfectly.
Me too. Me too.
No, you are not. Oh, yes. Okay,
Yes,
good.
yes, yes.
Probability of the signal coming back from you is low. So okay, perfect. Okay. So from now on, I call the minimization of this. I call the minimizer of this variational problem as Q of M. So this is a continuous object. This is a continuous function supported on like interval 0, 1. Then the theorem is as follow. If you take, so you see, the measure that I show you is converging to the Gibbs measure. So you see something, the process generated by the generator that I showed you previously. And by beta n, I mean that I take a sequence of temperature that are going to 0 with a proper speed. And I start with any initial condition, like I start with a specific configuration with a fixed mass m. Then for any positive epsilon, t goes to infinity, one for my dynamic. So here you should rescale the temperature with a parameter which grows faster than n. So you should go to the 0 temperature with a speed which is proper. So this is a discrete configuration. This is a continuous function. To compare them with each other, I take the linear interpolation of this object. And I'm here using a metric that's a pseudo norm that does not see the two initial symmetry that I was telling you. So I can use that compact concentration compactness type arguments. Okay, so this is in a split is a bit similar to those asymptotic stability results. So you start with any initial condition, and for you see, as you make, since the estimates here are most of them are uniform in n, for big N you should really consider that our dynamic when I'm beta this day, at least in this regime. Okay, but you should be careful that I'm first really taking the t to infinity and then n to infinity. So it's okay, important to do this, which is not very conventional. And okay, let me give a bit of heuristics. So the limit in t. So we did this mixing argument. And for the limit of n, we need some large deviation. Okay, when I'm rescaling the temperature properly, I'm concentrating on the 0 temperature manifold. And then I need to show the connection between the discrete 0 temperature manifold and the continuous minimizer. So for this large deviation estimate, a very important tools that I'm using is the discrete Giordani inequality. So this Schrödinger inequality is a so the continuous version of it is some Sobolev interpolation equality that you can bound the LP norm of a function with the gradient, different interpolations. Here I'm working on a torus, so I should add some other term here. And okay, then such that, okay, if you define them this way, then this is true for any n, and you do not see, so this C here is independent of n. So this is basically saying you that the potential energy is bounded by this gradient. And so you can control it by the gradient and the mass. So just a small comment is that this is really something crucial when you study NLS, nonlinear Schrödinger equation in the subcritical regime, because like global Wilposeness use this inequality and so on and so forth. Then I have a large deviation for the gradient. Okay, the large deviation that I'm showing is as follows. So when you are on a uniform, so this mu n is a uniform measure on the sphere of mass m. Then when you are on such a uniform measure, this gradient with this scaling that I chose, so I chose this scaling such that in the limit, I get the continuous approximation that I was showing before. So with this scaling, typically this measure will give you a gradient of order n square. But a gradient of order n square give you a very, using this inequality, you can deduce that such a huge gradient will give you surely a very huge energy, meaning that the e to the minus beta h will be extremely small. So the behavior of this measure is not dictated by the typical sets of this uniform measure for the gradient. So we are basically the typical configuration for the Gibbs measure are the very atypical configuration for this uniform measure considering this gradient. So in that sense, we need some proper large deviation estimate. And this large deviation is basically saying that, okay, the typical behavior is seeing something of order n square, but if I want to see something of order n to the power alpha with smaller alpha, I should pay a price of e to the minus n log n some constant. So this large deviation proving this large deviation is not hard. You can even obtain like other corrections, the next correction that comes at the next order, but okay, for our purpose it's rather easy. So you see, using this inequality and this large, okay, using this inequality you can okay, let me say this. You can basically see that the events that your gradient have being of order n to the power alpha is basically has the same probability of your event of your energy of n to the power alpha. And okay, this is can be computed up to some corrections with that large deviation estimate. And then you add the energy estimate here, and then you try to optimize over A. Then when you optimize it over A, you will see that, okay, if you rescale like beta n by n, you see rough configuration, namely like holder 1/2. So this is really corresponding that your measure is converging to some sort of a GFF, like the Gaussian free field. Okay, this is of order 1. Yeah, so it's not correct. Yeah. Sorry. Okay, this should be of order 1. Sorry. Okay, when beta n is of order n, meaning that you are taking temperature of order 1 over n, then you will have a smooth configurations, meaning that your gradient is smooth and you're getting configuration that, but you can prove that this configuration will not have the minimal energy. So they're gapped from the ground state. And okay, then okay, with this soft analysis, you can get some idea that how you should rescale your beta, and then for proving the lower bound for your large deviation later, you need some like more refined construction of the set of ground states that have the correct energy. Okay, and then the rest of the proof will be to connecting between the minimal energy discrete configuration and the continuous part. Okay, just to give a comment that in these works, there are some large deviations that at the first glance can be similar to our large deviation, but it's important if you look at them closely, if you rescale beta and m and n in different way, you get different physics, and then you get different large deviations. So the whole point is that here we are in some regime that is very different from those. Namely, we are in a regime that we force the configuration to be smooth by some rescaling. Okay, that was basically all about the heuristics, and let me give you about a very quick review about the other like future problem that one can consider. So the first thing is that the first natural question is that how you can like quantify the rate of the convergence. Okay, since it's a very degenerate noise, it's not a easy problem. So we are hoping that maybe using some kind of entropic hypocoercivity can help this a bit, but still, since it's a very degenerate noise, okay, I don't know. When the nonlinearity is 0, then the model and the dynamic is like when you concentrate on the when you condition on a fixed mass is very close to something people call the Berlin-Keck model. This model has some condensation, and it's interesting to see that how does our dynamic move this condensation. That's okay, we have some ideas. Then it's interesting to do the hydrodynamic limit for this model. It's a non-gradient model. So in that sense, it will be hard, but okay, we expect that in the diffusive time scale, we get some nonlinear diffusion. And the fact that we are a bit hopeful that to prove something for that is that the Gibbs measure is a Gaussian and is explicit. So we can do some decomposition into the focus space and then like control the higher non-gradient terms. Okay, the continuous counterpart. Okay, when I was making these slides, it was very long time ago. I had some hope to make these discrete things like giving some meaning in up to some renormalization. But as I spoke more with people who are expert in this field, I realized that our equation is too rough for doing such things, at least for the current technology. Okay, let me like summarize the most important related result. Is probably the most important one is this construction of the Gibbs measure. There are some large deviation estimate in this to work about the continuous Gibbs measure, which is in spirit is close to what we are doing. And okay, these are these two other work about the other large deviations. Okay, thanks a lot. And okay, I think it's a good point to stop.
Yeah. Thank you very much, Amirali. I hope everybody got the let's say the most of the talk. So, is there any question in the audience? I hope you can hear me, though. Can you hear me, Amirali?
Yeah, I can hear you not well, but I can understand at least.
It seems that Hubert has a question.
I cannot hear you.
Hubert, go on. Hubert, you are muted. You're...
Okay.
Okay.
Yes. Okay. So it's a simple question. You assume constantly.
There is maybe.
Hello. Yes. Can you hear me?
It seems I see.
No.
Yeah, there's a problem with your audio, and Hubert is asking a question.
Yeah, I'm listening, Hubert.
Okay, so yeah, so where does this restriction of p between 1 and 1 plus 4 over d comes from?
So you see, this is all basically coming from in this form of this inequality. Okay, so this inequality. Okay, let me show you another version, which is a bit better version. You can hear me, no?
Yes.
Hubert,
Yes, go on.
Can you hear me?
We can hear
Yes,
you.
I can hear you.
Okay, sorry. Okay, it's got so you see that you will get a positive power for p whenever we have this restriction. Okay, so
and does something special happen to the Gibbs measure when you cross this threshold of 1 plus 4 over d, or?
Yes. I think so you see that then you can have some blow-ups.
Okay.
Meaning that not true anymore. Basically, you should renormalize it. So you see, because basically the thing that the potential wants to do is concentrating you on one single point in a space, meaning creating something extremely irregular. These things can be circumvented by controlling it by gradient and Brownian object and so on. But when you do not have this tool, everything breaks apart.
Okay, yes.
So this potential.
The fact that you don't have this Gaillard-Nirenberg inequality.
Yeah, exactly.
Yeah, induce some blow up. Okay, and there is another thing. So you considered p equal 3. So like having p an even integer, an odd integer helps you, or is it? Why do you?
You see, okay. So basically, all the results that I'm saying is true for other p's. Okay.
Okay.
The only difference is that this minimization problem for other p's does not have a very nice unique solution. Meaning that, okay, if you want to be completely precise, then you should assume that not assume that. Okay. Let me put it this way. For p equal 3, we know that there is a unique minimizer for this minimization problem. Okay. For p is not equal 3, you can say some reasonable properties for such a minimizing manifold, and you prove convergence to such minimizing manifold.
Okay. Thank you.
Which is still a reasonable manifold.
Thank you very much.
Okay, so it seems that Marielle left us, so I'm assuming the sharing. Is there any other question in the audience? Okay, if not, let's thank Amirali again, and just remind you that we will continue on January 18. So now we stop. And
I just came back. Sorry.
Okay, great, Marielle. I give it to you back.
I just came back, but I don't know if I will be until the end.
So do you have questions, Marielle? Odo? Marielle? Okay, so it seems that Marielle has still problems.
Yeah, sorry. Yeah, it's okay. Thank you.
Okay. So thank you, Amirali, and we meet again on January 18. So goodbye, everyone. Have nice.
No, I'm okay. Thanks.
have
I'm okay.
Happy New Year, and see you next year in January 18. Bye-bye.
Okay. Thank